give this talk. This is really exciting. So when I, was invited to give this talk, I gave this incredibly long title, which is kind of absurd and out of control. But we can summarize this talk by this title instead: Diachroneity rules the Mid-Latitudes. So by the end of this talk, if you walk away with one thing, let it be this: Diachroneity rules the Mid-Latitudes. So let's dive in. Let me back up a little bit. This is based on a paper that my colleagues and I wrote and published. It was published last year, which is also called Diachroneity rules the Mid-Latitudes. It's a test case using late Neogene Planktic Foraminifera across the Western Pacific. So I wrote this in collaboration with Martin Crunwell, who's at GNS Science in New Zealand, Mark Leckie, who is my PhD advisor and still a good friend and collaborator at UMass Amherst. James Albanese was my undergraduate student that I worked with while at UMass. He did some validations, data validation for the study, and it was kind of the beginning of it. And then Jacob Uzel, that's my husband. He's an excellent helper. I roped him into this project while we were during COVID. So just some background on how I got started with this project. In 2020, Mark and I published our paper in PLOS One, where we made biozones for the Northwest Pacific Ocean. So I was working across these three holes in the Northwest Pacific that cross the Kuroshio Current Extension, this major western boundary currents. So these were holes 1207A, 12088, and 1209A on this modern-day sea surface temperature map. They're denoted by these black stars. So the biozones that we created are present on the right side of your screen. So this is just geologic time and age, millions of years, period, epoch, stage, then New Zealand epoch and stage names, magnetostratigraphy, the major crons. So hole 1207, we applied the temperate zonation scheme. At hole 1208A, the temperate zonation scheme as well, but at 1209A, this more southern site, the subtropical zonation scheme, and we were able to tie those in with the global tropical to subtropical zonation schemes developed by, revised by Wade and others in 2011, and then further updated by King and others in 2020. And then also the calcareous nanoplankton zones are plotted here. So you'll see this figure again later. But we noticed when I was doing this study that there is diachroneity of these datums that we use to construct these biozones just within the Kuroshio Current Extension region. And these three sites lie within about 10 degrees of latitude with one another. So that's kind of interesting. So I moved here in August 2019 to do my postdoc at Binghamton University. It flipped to tenure track just this semester. But during January 2020, everything shut down. So I was going to do more fossil-informed geochemistry and specialize in that. But with lab shutdown, that wasn't possible. So my husband and I were in lockdown in our apartment, and I thought, you know what? This is a really good opportunity to start investigating diachroneity of fossil specimens at a larger geographic scale. So Harry Dowsett in 1988 had published this really great paper where he did investigate diachroneity of fossil datums in the Southwest Pacific Ocean. Specifically, he was looking at Planktic Foraminifera and calcareous nanoplankton datums. So he used the leg 90 sites, so sites 586 through 592 in the Southwest Pacific. They form a transect, and he found that datums were diachronous by about 500,000 to 800,000 years. So that's a lot. But I love this quote from his paper that I just pulled out. He says, "The results of this study indicate the hazards of creating age models based on final events that have been calibrated to a timescale in some other region." And this really got me thinking. If we have diachroneity of fossil first and last appearances that are really apparent at the 5 sites that Harry used in his study, these sites span 36 degrees of latitude. What does that mean for diachroneity of fossil datums across ocean basins or even across hemispheres? So the objectives of the study I came up with were really to quantify diachroneity of planktic foraminiferal species, specifically those that are used in biostratigraphic zonation schemes. So I wanted to investigate diachroneity within regions, also among different regions, and also regions. I wanted to compare the tropics of the Western Equatorial Pacific with the tropical to subtropical zonation scheme of King and others 2020, the ages of those datums, to see how those differed. We also wanted to see how diachroneity affects foraminiferal biozonation schemes, and also hypothesize what are the main drivers, what are the underlying drivers of these diachronous patterns that we were beginning to see. So we use this transect of sites across the Western across the Western Pacific. So these are the sites. This is a modern day sea surface temperature map. So we use sites from Ocean Discovery Program like 198. So these are the sites that I used in my dissertation, 1207A to 1208A. We also use sites from ODP leg 130, specifically hole 806B. So that was our Western Equatorial Pacific site. And we also use the leg 90 sites that form a transect from the tropics. So 586B is a hole that's very close to 806B, all the way down to site 593, which is lying in more temperate or subpolar water masses. So these sites span from about 38 degrees north to 40 degrees south. So we're capturing the mid-latitudes of both the northern hemisphere and the southern hemisphere, as well as across the tropics. But what's also cool about this transect is we're capturing changes across these major water masses. For example, in the Northwest Pacific, we have the Croceo current extension. So very sharp temperature gradients, very sharp salinity gradients. And in the southern hemisphere, we have the Tasman front, which is an eddy system, but we also have these water masses that are set up from Antarctic ice growth. So once we had our sites, I also had to update the age models for all of those sites, and I updated them to the geologic timescale 2020. For DSDP leg 90, we use calcareous nanoplankton biostratigraphy to form the age models. We also use bulbiform biostratigraphy. That was really important in the Miocene sections. So Martin Crundwell and his colleagues at GNS have been implementing a lot of bulbiforms and calibrating their ages for use in biostratigraphy. And then some of the sites have magnetic reversal boundaries, so we incorporated those where we could. For leg 130 sites, so hole 806B and the Western Equatorial Pacific, that site's on a bathymetric high. It's very tropical. There's a lot of carbonates, so no magnetic reversal boundaries. So we were only able to use calcareous nanoplankton biostratigraphy to construct that site's age model. And then the leg 198 sites, so hole 1207A, 1208A, and 1209A, they're very closer. Well, they're closer to land, but they're also in deeper water. So they have a really nice carbonate, but also clays throughout the sections. So they have really, really well-constrained magnetic reversal boundaries. So they have a really nice age model based on magnetostratigraphy. So the figure on the right side of your screen is the age model from hole 1207A, and those red X's or crosses are where we have magnetic reversal boundaries and age control. So really nice. I will also add that my colleagues here at Binghamton and I are working to tune this section of hole 1207, especially within the Pliocene, and hopefully we can pull that back into the Miocene a bit. We also had to update the taxonomy at all of these sites and these holes that we were using. And what we did was use the paper that Mark and I published in 2020 in Micropaleontology. It was a major update to late Neogene Planktic Foraminifera, especially in the mid-latitude region. So that was based on our leg 198 sites in the Northwest Pacific. So we applied our taxonomy to all of the sites. For species that were ranging from the Oligocene into the Neogene, we also used the Oligocene Atlas published by Wade and others in 2018. And then old reliable Kennett and Sternavase in 1983. We have to use that as well. So there are still some taxonomic uncertainties within our taxonomy. I will note that it's always in flux, but stay tuned for the work of the Neogene to Quaternary Planktic Foraminiferal Working Group. We're working on that actively and in the coming years to update taxonomy. So for this study, we only wanted to investigate species that were commonly used in biostratigraphy to construct these biozones. Didn't want to investigate all species that would get a little out of control, and also because I wanted to compare species that occur both in the tropics and the mid-latitudes. So we also looked for species that kind of occurred at most of these sites. So we pulled the primary and secondary datums in the late Neogene from the tropical and subtropical zonation scheme that was updated first by Wade and others in 2011, and most recently by King and others in 2020. And that's part of the figure you're looking at on your screen on the right side. And we also used the primary datums that were very prevalent in the mid-latitude zonation schemes. So those schemes that were developed first by Kennett in 1973, that were later updated by Jenkins and Srinivasan in 1986, and then Mark and I's datums that we developed for the Northwest Pacific. And we pulled those primary datums simply because we don't have secondary datums in the mid-latitudes. So we ended up with 31 species in total to investigate in this study, and 43 datum events were investigated. So while our brains are tuned into biostratigraphy and looking at biozones, let's just start there. So what you're looking at are the Planktic Foraminiferal biostratigraphic schemes, and I'm going to step you through each of these sites and show you the biozones that we applied. I showed you this figure on a few slides back, but again, on the left side, we have age in millions of years, the global period, epoch, and stages. We also have the New Zealand epoch and stage names, magnetostratigraphy, and major crons. And then what you're looking at on this screen are the 3 Northwest Pacific sites from leg 198. So at hole 1207A and 1208A, we applied the temperate biozonation scheme, and at 1209A, we applied the subtropical zonation scheme. And this is from Mark and I's paper that we published in 2020. So what I've highlighted here is a base of Truncatulinoides, which defines the Truncatulinoides lowest occurrence zone. And you can see that among these 3 sites, the base of that biozone is diachronous. I've also highlighted the base of Hirsutella margaritae, again, super diachronous. So let's now add in the Western Equatorial Pacific tropical sites. So these are sites 806b and 586b. They lie very closely together. However, their biozones are quite diachronous. So I should also say we applied the tropical to subtropical biostratigraphic zonation scheme to these sites. That's from King and others in 2020. Again, the top of toe census, incredibly diachronous among these two sites. The base of Marguerite, also very diachronous. I think this is probably related to an age model issue though, because these sites are located so close to one another. Lastly, we added in the sites, the leg 90 sites from the Southwest Pacific Ocean. So site 587 and 588, we both applied the warm subtropical zonation scheme. At sites 590, 591, and 592, they worked with the cool subtropical biozonation scheme. And then at site 593, which is our most southern site down here in the southern hemisphere, we applied the temperate zonation scheme. And those were the biozonation schemes developed by Kennett in 73 as modified by Jenkins and Srinivasan in 1986. And lastly, what we can do, let me go back just a bit. Here's the base of Troncachulinoides again, that's defining some of these biozones. Again, very diachronous. Lastly, we can plug all of these into the global tropical to subtropical biozonation scheme developed by or updated by King and others in 2020. And the calcareous nanoplankton zones are also here. So here's the base of PT1b, that biozone, and we're comparing it to these Western equatorial Pacific sites. Again, quite diachronous. If we look at the base of biozone PL2, again, very diachronous. So what we're seeing just from this overview of biozones across these sites is that we're seeing diachroneity of biozones within the same regions, diachroneity among different regions, and then diachroneity between our tropical regions in the Western equatorial Pacific, compared with the dates of datums in the tropical biozonation scheme that is in use today. So now let's dig into these patterns a little more and investigate what's going on. So these first few slides, I'm going to show you patterns of species first occurrences. So what you're looking at now on the left side of your screen is age in millions of years. And then you're also looking at global epoch and stage names here as well. And then our sites that we used in the study. So they go from highest latitude in the northern hemisphere to high latitude in the southern hemisphere. So 1207, 1208, and 1209, these are Northwest Pacific sites. 806b and 586 are our Western equatorial Pacific sites. 587 through 593 are our Southern Hemisphere leg 90 sites. And the site that says tropical right here, that indicates that these datum dates are from the tropical to subtropical zonation scheme from King and others 2020, the one that's widely in use today. Every species is listed here. I've split them into different groups on different figures. But every species has its own color, its own symbol, and its own line style to hopefully make it a little easier to see. Sometimes these things look like a pot of spaghetti all mixed up, but I'm just going to point out a few of these patterns very quickly. So I want to pull your attention to Globigerinola callida, which is highlighted by the blue box here. This is a species that appears first in the Northwest Pacific, and then it later appears in the tropics, and lastly in the Southwest Pacific. This dispersal style, where it appears first in the Northwest Pacific, is actually very uncommon in this data set. There are also species such as Polyneatina primalis that appear first in the tropics. So here's our tropical site that's appearing here first, and then later migrate into the southern hemisphere and into the northern hemisphere. So we have this kind of occurring in the tropics and then going to the going to the mid-latitudes. Some other first occurrences that we'll look at. Now we're looking at globocannelids, some globoturborhodolidas on here as well as Neogloboquadrina. But I want to draw your attention to the globocannelids. So here's Inflata, Puncticulata, and Conomyosia, denoted by these green boxes. So the globocannelids first appear in the southern hemisphere in the Southwest Pacific Ocean, and then they later migrate into the northern hemisphere. So here's Inflata with the purple line and purple stars. So it's very apparent that it appears first in the southern hemisphere, in the higher latitudes, and then it has this like jump or step up into the northwest or in the northern hemisphere, the Northwest Pacific, and then later appears in the tropics. These species, Conomyosia, does the same thing. It occurs down here in the southern hemisphere first, and then leaps up into the northern hemisphere. And note also Conomyosia, the base of this species, it occurs firstly in the Miocene of the southern hemisphere. And then when it jumps into the northern hemisphere, that occurs in the Pliocene. Okay, so now we're going to look at some first occurrences. And I really want to draw your attention to Troncorotalia. More first occurrences. So these are species that are occurring first in the Southwest Pacific Ocean. So here they are, but they then migrate into the tropics and then into the Northern Hemisphere. So they don't exhibit this like jump pattern like some of these global cannelids do, where they appear in the Southern Hemisphere and then jump into the Northern Hemisphere. Rather, their dispersal is more gradual from one hemisphere into the other. Now we're going to look at some last occurrences really quickly. What I've highlighted here in the green boxes are Globogerinoides extremis, Polyneotema primalis, and Globogerinoides obliquus. So these first disappear from the Southwest Pacific, and these species constrict their range into the Northwest Pacific. So, and also across the tropics. So there's this clear pattern of range constriction before they finally go, well, we can't say for sure if they're going extinct in the Northern Hemisphere, but their last appearances in our data set are in the Northwest Pacific Ocean. One other species I want to draw your attention to is Globoquadrina dehiscens. This is a species that has a very interesting pattern of last occurrences. So this is a species that has always kind of been known to approximate the Miocene-Pliocene boundary in the tropics. However, that's not true for the mid-latitudes. This species in the mid-latitudes is actually more approximating the late to middle Miocene. It then constricts its range into the tropics, and its last occurrence is near the Miocene-Pliocene boundary. So that's pretty astounding pattern that we pulled out of this data set. So there's two major dispersal styles that we were able to kind of denote or infer from this data set. The first, which is denoted by this green boxes around these species names here, is this gradual dispersal that happens from the Southwest Pacific into the Northwest Pacific. So we can see this with the base of Truncortalia truncatulinoides. Here in the blue, it kind of slowly or kind of gradually does this dispersal. It's all being contained within the Pleistocene. But there's also this other kind of stepwise dispersal from the Southwest Pacific into the Northwest Pacific. So these are species like the global cannelids are doing this. Globogerinoides extremis is also, you could say, an extreme example of this. But it's here in the tropics and the mid-latitudes of the Southwest Pacific, and then it leaps up into the Northern Hemisphere in the Northwest Pacific Ocean. So now that we've looked at these dispersal styles, let's try to put some hard numbers into these and actually quantify the Diachroneity. So first, we're going to start with within regions. And we're going to start with the Northwest Pacific Ocean, looking at holes 1207A, 1208, and 1209A. So the average Diachroneity of datums within this region is about 1.39 million years. And that's taking its latest occurrence date with its earliest occurrence date, just subtracting those two. The base of Neogloboquadrina costensis has the highest Diachroneity within this region at 6.18 million years, but the base of Globoturborotolita decorapatura has the lowest Diachroneity within this region at 0.2 million years. Now we're going to look at the Southwest Pacific Ocean, so the leg 90 sites, excluding site 586b, so just down here in the mid-latitudes. The average Diachroneity of datums in this part of the Southwest Pacific is 2.05 million years, so quite a bit more than the Northwest Pacific. The top of Seminiolina has the highest Diachroneity at 9.35 million years. That's pretty big. The base of Nepenthes has the lowest Diachroneity within the region at about 110,000 years. And now we're going to look at the Western Equatorial Pacific. Average Diachroneity of these datums within that region is about 800,000 years. Minardella multicamerata has the highest Diachroneity at 4.73 million years, but Fistulosa is pretty isochronous between those two sites, and that's pretty good. But again, these Western Equatorial Pacific sites are incredibly close together. 4.73 million years is really high. There might be an age model issue, but you know, this 9.35 and 6.18 million years, that's also quite high. So I also wanted to look at Diachroneity between the Indian Ocean and the Western Equatorial Pacific. So Groenveld and others in 2021, recently they published this paper looking at this suite of sites off the northwest coast of Australia. And one of their sites, IODP site U1463, they also calibrated Planktic Foraminiferal events there at that site. What's really great about their site is that they have an orbitally tuned age model. So this was a really phenomenal opportunity to compare their datum dates to hole 806b in the Western Equatorial Pacific. So the average Diachroneity of datums between our study, so site, hole 806b in the Western Equatorial Pacific and site U1463 was about 500,000 years. Highest Diachroneity was the top of Kochi at 1.85 million years. Lowest Diachroneity was the base of Tosensis, which was nearly isochronous between the two at 10,000 years. We also wanted to compare the datum dates between the Indian Ocean at site U1463 with the tropical and subtropical datum dates presented in King and Others 2020. Average diachronicity between these two, well, that site and that zonation scheme, were about 400,000 years. The highest diachronicity, again, is Kochi at 1.35 million years, and extremist is pretty isochronous between the tropical-subtropical zonation scheme and site U1463. While I was making this talk, I also stumbled across another paper that was recently published by Raman and others. And what they did was look at late Pleistocene and also did biostratigraphy within the Mentel Basin. So this is off the southwest coast of Australia, site U1516. And just from their abstract, I really pulled out this little excerpt that they had. They said the Planktic Foraminiferal datums marked in hole U1516b are mostly synchronous with datums reported in the southern hemisphere, but are diachronous with datums in the northern hemisphere. So other authors are catching on to this, and they're also showing that there is a diachronicity of these datums between the southern hemisphere and the northern hemisphere. We also wanted to look at diachronicity of datums between the western equatorial Pacific site, so our site 806b, and the Atlantic Ocean. So within the tropical to subtropical biozonation scheme, the one that was recently updated by King and others 2020, from Wade and others 2011, it contains several datum events that were calibrated from ocean drilling program site 925. And this is a figure from Yasuhara and others 2020. It's a really great location map showing that this site is really within the western equatorial Atlantic region. And Sarah Rice has been used in a lot of evolutionary studies as well. But my question was, is there diachronicity between the western equatorial Pacific and western equatorial Atlantic? So diachronicity of datums between hole 806b and those calibrated in this tropical to subtropical biozonation scheme at site 925, they're on the range from 0.18 to 3.86 million years. So I've summarized a few of these species that have diachronicity in this table below. So the highest, well, I'm not showing you the highest, but these are some more moderate values. The base of dehiscence, there's a difference of almost 1 million years between the western equatorial Pacific and western equatorial Atlantic. Some other high ones are the top of Marguerite, that differs by about 760,000 years between these two sites. And the others here are on the range of about 400,000 to about 500,000 years. So that's quite diachronous. So it's worth asking yourselves, are there local oceanographic differences that are causing diachronicity between the western equatorial Pacific and western equatorial Atlantic? Are the Sarah Rice datums just not appropriate from the western equatorial Pacific? Is it an age model issue? Site 925 Sarah Rice has a tuned age model, but hole 806b's age model is based on solely calcareous nanoplankton biostratigraphy. There could also be a bit of taxonomic issues coming into play. Different micropaleontologists have identified species in the western equatorial Pacific. That was done by Mark Leckie and his first PhD student, Bill Chason, compared to the western equatorial Atlantic, which were identified by different micropaleontologists. So it's something to think about and chew on for us. So now that I've showed you that, I also want to go and think about drivers of dispersal and causes of these patterns of diachronicity. So these species that we're looking at, they seem to appear first in the southern hemisphere, and then later they appear in the northern hemisphere. So I'm showing you this figure that I showed you previously, where these two different main dispersal styles, but it's very clear from these species that I've picked out that they're evolving in the southern hemisphere and then later migrating into the northern hemisphere. So what we're hypothesizing is that maybe conditions in the Southwest Pacific and the southern hemisphere were more viable for reproduction of planktic foraminifera and allowed them to establish really robust populations before environments in the Northwest Pacific were available for them to really establish robust populations. So the hypothesis here is that several species may have evolved or appeared first in the southern hemisphere or Southwest Pacific, and that was stated by Jenkins in his 1992 paper. And this may be due to the growth of Antarctic ice and the establishment of oceanic fronts within the southern hemisphere related to expansion of Antarctic ice. And that was a hypothesis that Kennett put forth in his 1977 and 1978 papers. And this is something we pretty much agree with. So what you're looking at on the left side of your screen is just a figure from Crundwell and others in 2008. Martin does fabulous images where he shows these frontal zones and these currents around the Southwest Pacific Ocean. So you can see that there's quite a lot of frontal systems here and different water masses as well. And that all developed in response to Antarctic ice and cooling of the Earth. Now, I'm showing you on the right side of the screen, this is data from the last chapter of my dissertation that is currently unpublished. Hopefully we get that out this year. But what I did was look at the global canelids, and I chose 30-something sites around the globe, updated their age models, not using Planktic Foraminiferal biostrat because I wanted to compare datum dates and occurrence dates between these species. And we wanted to investigate how they dispersed on the global scale and where was it that they were first evolving. So what you're looking at is the global oxygen 18 from benthic foraminifera, the stack, with a phylogeny of the global canelids. And all of these little symbols and dots in different colors represent different ocean basins and different locations and regions that we split out. But notice the first occurrence of all of these species, they all occur in the southern hemisphere, in the Southwest Pacific, some in the South Atlantic Ocean, and some in the Indian Ocean. So we do agree with the hypothesis of Jenkins and others, Jenkins in 1992, that at least for the global canelids, a lot of these species are evolving first in the southern hemisphere. Okay, we're also seeing this pattern that when species come from the Southwest Pacific into the Northwest Pacific, they will first appear at holes 1207A or 1208A. These are our highest latitude sites in the Northwest Pacific Ocean. Today, these sites are located within the Kuroshio Current extension, and hole 1207A is located on like the northern edge of that current. Later, those species will then disperse southward into hole 1209A, which today is lying in subtropical water masses. So on the left side of your screen, this is all kind of a lot to digest, so let me just step you through it for a minute. On the left side of your screen is this out of control figure that I made for my 2021 paper, where we were reconstructing the Kuroshio Current extension for the last 5 million years, well, from about 5 to 2.5 million years. But we were going across the warm Pliocene and importantly, the mid-Pliocene warm period. So here's the mid-Pliocene warm period. Here's our 3 sites, the geochemical data from them. And here are 3 sites on a modern day sea surface temperature map. The Kuroshio Current today kind of goes across hole 1208, 1207 is on the northern edge. But we hypothesized from our geochemical data that during the warm Pliocene and during the mid-Pliocene warm period, the Kuroshio Current extension either warmed or it shifted northward, which brought more subtropical water masses washing over sites 12088 and 1207A. So this red bar in this little reconstruction cartoon down here represents the location of the Kuroshio Current extension. I'm also showing you preliminary data. Well, it's not preliminary data from my master's student, Charlotte. She's going to defend actually next month, but she's done high resolution stable isotopic analyses at hole 1207 across the mid-Pliocene warm period. So we're investigating the response to this current from the view of the thermocline. We're using global canelid inflata here. It warms up really intensely, very quickly across the mid-Pliocene and kind of stays warm throughout this interval. So again, we are hypothesizing that this current warms. So what we think was happening is that this warmer water, when we had an expanded North Pacific subtropical gyre and a Kuroshio current, these western boundary currents that were moving northward, these warmer waters brought species to higher latitudes first. And that's why we're seeing them appear at 1208 and 1207 first. And they later dispersed southward into hole 1209. We also think that northern hemisphere ice sheets, that formed later than Antarctica, that also allowed for more dispersal of species into the mid-latitudes of the northern hemisphere that maybe would have set up some more water mass boundaries in the northern hemisphere, also setting up different niche space for those species to finally disperse into and establish robust populations. Okay, so let me switch gears a little bit here, and you're probably asking yourselves perhaps, why does any of this matter? Like, good grief. So Planktic foraminifera are used in biostratigraphy for first order age control, both in deep sea sedimentary sections and also outcrops and on land sections. So we need to have detailed knowledge of when they evolved, when they went extinct, and their first and last appearances on a regional scale. That's all critical feeding into biostratigraphic knowledge. If we have incorrect ages of fossil datums at a regional scale, that can lead to really wrong interpretations where we're trying to build a more robust age model, for example, built on magnetic reversal boundaries. If we have incorrect ages for these fossil datums, that could put us within the wrong paleomagnetic reversal. For example, in the middle Miocene, Earth's poles were flip-flopping like a fish out of water. So those reversals are happening very quickly. So we need to have it nailed down very precisely when these species were evolving and going extinct or appearing and disappearing in that regional scale. Also, if we want to do orbital tuning, we also need to know very precisely when these species were evolving, going extinct, appearing, disappearing. And also, when we have the incorrect dates for when these species have their first and last occurrences, that can mask true paleobiogeographic patterns of dispersal styles, but also evolutionary types. And that kind of research is really imperative to infer how species and populations of marine plankton are going to continue changing under an increasingly warmer planet, because we can investigate their paleobiogeography and their evolution in previous warm periods. So I want to pause here and say that diachroneity is an absolute strength of the Planktic Foraminiferal record. It is absolutely not a weakness. So the underlying drivers of Planktic Foraminiferal diachroneity that are causing these species to disperse into different regions at different times, those drivers are incredibly informative to speciation and dispersal processes and how they occur in the open marine realm for marine plankton. So there's 3 studies here from my awesome fellow early career colleagues. The first study on the left side of your screen is by Adam Woodhouse and Anshuman Swain. They just published recently in Nature. And what they did was a neural network analysis, and they found that Planktic Foraminifera shifted towards the tropics in a cooling world. So that's incredibly informative. They're looking at these paleobiogeographic patterns on a global scale. Bascolo, Galaza, Crichton, and others, and their colleagues in 2021, they also did a study looking at Lake Neogene Planktic Foraminifera, and they found that increased food delivery to the thermocline regions opened up new niches for planktics during that time and allowed them to occupy deeper water depths. Another paper published by Fenton and others, also published recently in Nature, they looked at the latitudinal diversity gradient of Planktic Foraminifera from the Eocene into the Pleistocene, and they found that the modern-style latitudinal diversity gradients developed about 15 million years ago. So again, really awesome data, really global data set. So these are kind of the underlying drivers, these patterns of climate that are causing diachroneity. It's not a weakness, it's a strength. Okay, so, but what can we do about it? So this is my plea to all the other biostratigraphers and taxonomists out there to meet me in the middle, latitudes. We have a big need for regional, mid-latitude, high-resolution Planktic Foraminiferal biostratigraphic zonation schemes. So I've kind of showed that throughout this research that I've done. Even if we use the same biozonation scheme at similar sites, those ages may be a bit wrong. We also have a need for robust age models constructed using magnetostratigraphy and or orbital tuning, for example, or even geochemically formed, for which we can calibrate datums against for use in biostratigraphy. So we really need tight first and last occurrences of these species. And there's also a need for revised taxonomy in the Neogene through Quaternary, especially of these morphos types and species that are occurring within the mid-latitudes. Now, this is something that I've worked on. Others have started working on kind of all of these as well. In this last point, the taxonomy, it is in progress by the Neogene to Quaternary Planktic Foraminiferal Working Group. So stay tuned for that. Okay, just some future directions to start wrapping this up. I'm currently involved with a project where we're going to start data cleaning within the Triton database. So this is a big update to Planktic Foraminiferal global occurrences. It was published by Isabel Fenton and Adam Woodhouse and others in 2021. So what we're finding by playing with the data in Triton is that we have some anomalous occurrences of species. So for example, species that should be confined to the P alpha zone are actually occurring in the Oligocene. So as you can imagine, that may affect paleobiogeographic patterns and measures of diversity. So I'm working on this with Andy Frost, who's leading the paper, Mark Leckie, Adam Woodhouse, and Isabel Fenton. So once we get that cleaned up, we're also going to continue conducting paleobiogeographic analyses from the global Planktic Foraminiferal data sets, so using Triton, for example. So on the left side of your screen, I'm just showing you a little sneak preview of this data. These are data that Andy coded up, pulling the data in from Triton into R. So there's age on the left from 0 to 60 million years. And on the x-axis here is paleolatitude. And what we're looking at are the occurrences of global Quadrina dehiscens. So I showed you this earlier in this talk based on the data set. It has its latest last occurrence here in the tropics. And then we have this kind of pattern of where its last occurrences occur in the Miocene towards the mid-latitudes. And that's exactly what we're seeing here, again, on a global scale. So I also want to continuing investigating diachroneity and paleobiogeographic patterns with additional sites. For example, I recently sailed, well, I didn't sail, couldn't get a flight out. Long story short, I worked from home this summer for Expedition 393, but we're going to be pulling in additional sites and investigating diachroneity of Planktic Foraminiferal species. So my PhD student, Ravi, will be working on that. And generally with my lab group, we want to continue creating regional mid-latitude Planktic Foraminiferal biostratigraphic zonation schemes from these sites with robust age models. And that's something I hope that, others are working on as well. And I know some folks are out there working on it at the moment too. So some conclusions. Again, If you remember this talk, remember diachroneity rules the mid-latitudes. So diachroneity of planktic foraminiferal datums are apparent within regions, among different regions, and also between the Western Pacific sites used in this study, so like hole 806b, compared to datum ages from the tropical to subtropical zonation scheme by King and others 2020. And there's also diachroneity apparent between the Western Pacific and the Indian Ocean. Diachroneity is likely driven by climatic patterns and probably tectonic events too. So expansion of Antarctic ice, the development of different weather masses in the Southern Hemisphere, expansion of these subtropical gyre systems and their associated Western and Eastern boundary currents during times of global warming, and also perhaps later ice growth and cooling of the Northern Hemisphere compared to the Southern Hemisphere. So we have a need for sedimentary sections with robust age models for which we can calibrate datums in the mid-latitudes. The mid-latitudes probably need their own regionally based biozonation schemes. So again, these are probably going to need to be regional in nature. We cannot take the Southwest Pacific schemes and apply them to the Northwest Pacific without some modification. And even the ages of the biozones themselves will change because of the diachroneity of planktic foraminifera. And lastly, and importantly, diachroneity, it's absolutely not a weakness of the planktic foraminiferal record. It is a strength that is driven by and underlied by climate and tectonic patterns. And those patterns of paleobiogeography that lead to diachroneity are incredibly important and incredibly relevant to today. So with that, I'll end. Thank you all for coming and listening, and I'm happy to take any questions.
Thank you, Adriane, for an excellent talk. Do we have any questions from the audience who is still uploading to you?
Oh, go ahead. Thank you all. Yeah, and I'm happy to reshare any slides or any part of this talk if you want to look at more data or talk about it.
Thank you very much. While people thinking, if you have a question, please raise your hand. Otherwise, me and Jamie, we cannot see you. We have one question in the chat from Tom Dines, who writes, for those sites showing intra-regional diachroneity, were multiple samples, same depth, processed, examined very often or ever?
Multiple samples, so the same depth. Probably not. So this is another kind of limitation of the study, and this talk was already getting kind of long, so I didn't want to keep going with the limitations. But so a lot of those leg 90 sites, they're based only on core catcher samples, and they weren't processed. They were processed according probably on the ship. So they're using that kind of like ship method of quickly looking at them. So that's the Jenkins and Srinivasan 1986 paper comes from that. So and then the whole 806b in the Western Equatorial Pacific, that biostratigraphy was conducted by Chason and Leckie in the 90s sometime. They didn't reprocess any samples, but they did look at samples at a higher resolution. And for my work in the Northwest Pacific, based on the leg 198 sites, no, we didn't process multiple samples from the same depth. We were taking 10 cc's and just processing them and just looking through as much of those samples as we could to nail down species first and last occurrences.
Thank you, Adriane. I think Chris was next in line, and then Adam. Chris, would you like to ask a question yourself?
Yeah, thanks. Adriane, that was a really cool talk. Thank you for that. I was wondering, you talked briefly about, one of the sites was based on a calcareous nanofossil biostratigraphy. And it got me thinking about, like, do you have any idea if calcareous nanoplankton have similar levels of diachroneity? Like, are there any nanofossil taxa that are 9 million years apart from the mid-latitudes to the tropics?
Yeah, that's a really great question. It's a really important question. I don't know. So Harry Dowsett in that 1988 study, right, he showed that there are diachroneity of these calcareous nanoplankton datums. And I was like, ooh, that's really important and interesting. So yeah, if there's any calcareous nanoplankton people on the talk that want to work on that, like, I think that is something that is incredibly important to think about, and something that needs to be addressed head on as well, because I'm not sure, and I haven't really dug into that literature, but yeah, incredibly important. Thanks for that, Chris.
Thank you, Chris and Adriane. Adam, I think it's your turn now.
Hello, yeah, really great talk, Adriane. That was awesome.
Thank you.
Brian Huber and others showed that in the immediate aftermath of the KPG mass extinction, that the southern hemisphere seems to exhibit endemism as well. So what are your thoughts on whether or not the Southern Hemisphere has always been this kind of cradle for certain types of planktonic foraminifera, even in a world dominated by a greenhouse world, not just a world with ice sheets?
Yeah, that's another great question. It's something I've thought about. Yeah, I love Brian's paper. It's really great. And like to see that kind of endemism that deep in time was like really cool. But also it kind of makes sense with tectonics and different configurations. So that's one of the things I want to do next with this research in my research group is take this research back in time. So we're only looking at the last 15 million years of Earth's history. So we're just across the late Neogene. Certainly there are other major climate events like the EO boundary, right, where we have Antarctic ice expansion, all kinds of different times in Earth's history. So where is diachroneity pronounced? Where is it less, where is it reduced? These are questions that I really want to start answering and digging into with my lab group and kind of investigating like, okay, what were causing these at different time periods and were the drivers different or similar to the late Neogene? So to answer your question, I'm not sure, but I'm really interested in that question and I've definitely thought about it. So yeah, thanks for that, Adam.
Thank you. Adam, do you, okay, I see you're happy with the answer. Helen, would you like to ask your question, please?
Yeah. Hi, Adriane. Very nice talk. Thank you. Just one. Can you hear me?
Yes. Yep.
Yeah. Okay. Just one. This idea of the Southern Ocean producing species. I don't know. I think Kate Darling. I was talking to her recently, and the genetic data say exactly that. That
Ooh.
these strong fronts. Strong frontal systems are the cradle of speciation in a way, and they just from time to time spit these things out, especially once you've got really strong gradients, climatic gradients. So that's really interesting that you see that in your data as well. I won't say anything more because I don't know. I'll probably dig myself a hole, but I certainly heard her say that. My second question was, so if this diachroneity is, you're seeing it strongly in your Neogene perspective, would you predict it's worse in the Neogene once you've got gateway closures, strong gradients compared to an Eocene world, for example?
Yes, I would predict that yes. So even a lot of diachroneity that we're seeing between the Western Equatorial Pacific and the Western Equatorial Atlantic, a lot of that is happening when we're having constriction of the Central American Seaway, the CAS. So that's beginning to close. So that's shutting off a major gateway that's allowing, it allowed Pacific surface ocean water and Atlantic surface ocean water to exchange through that gateway. So once you close it, you're ramping up your western boundary currents, your gyre systems are kind of kicking in, but that's also cutting off potentially a, major dispersal pathway. So Andy Frost, Chris Lowry, and a few others published a paper about Kugleri and how it was diachronous between the Central American Seaway because they think of that closure that was happening. So absolutely, I think it's absolutely kind of related to mostly locked into this cooling, this bi-hemispheric cooling that starts to occur and you set up all these frontal boundaries, you increase the latitudinal temperature gradients. And I would expect that in a warmer world like the Eocene, that because those gradients are reduced and you have less ice, that you would probably reduce diachroneity as well. Yeah, that's a great question.
Certainly the morphologies that you find spread out across the global ocean in the Eocene seem to be more similar. I don't know.
Exactly.
So I've got a PhD student, Teja Weitkamp, who's we're doing kind of exactly what you proposed in terms of looking at biostratigraphy in the high North Atlantic. Awesome. Another serious problem area in terms of taxonomy, application of biozonation. So yeah, we're with you on that.
Oh, amazing. That's great to hear. Okay, cool. I look forward to the results of that. That's amazing. Yeah. Thank you for those, Helen.
Maybe see you at Forams in Perugia.
Yeah, I won't be able to go, unfortunately, but I will be with you all in spirit.
Okay. Thank you very much.
Thank you.
Thank you, Helen and Adriane, for nice discussion. We have a question in the chat. I see Tina has a question. Tina, would you like to ask it by yourself? No. Okay, Tina writes, thank you for the talk. How about reflectivity of diachroneity pattern using benthic forams proxies?
Ooh, so the diachroneity of benthic foraminifera, I think if I'm understanding that question, I don't know. So bottom waters are an entirely different beast compared to the surface currents. They're doing different things, but that's also something that's locked into the expansion of Antarctic ice. So Antarctic bottom water, we have this North Atlantic bottom water. There's been papers put out recently by Heather Ford and colleagues that say that during the Pliocene, perhaps we had deep water formation in the North Pacific Ocean rather than the North Atlantic. So all of that is really interesting and would certainly contribute to the diachroneity of benthic foraminifera if we're using them for biostratigraphic studies. I know in the Southwest Pacific sector, the New Zealanders, the Australians, they do use benthic foraminifera to calibrate their age models sometimes, just because they have a lack of morphospecies down there, which is another interesting issue or phenomena, I should say. It's not an issue. But yeah, I haven't thought as much about the benthic foraminifera, but that is honestly something I'd be interested in seeing as well. So for the benthic forain people, it's definitely something cool to investigate as well. Thank you for that.
Thank you, Adriane. Do we have any more questions? We still have 10 more minutes. Last chance. Nobody's volunteering. Okay, but then we thank you, Adriane, very much for excellent talk, and thank you for agreeing to give seminar.
Absolutely. Thank you all so much
And
for
then,
the invitation.
yes, and then hopefully see you at the next seminar in April. And by the way, guys, we're looking for volunteers to run the seminars in the future, because as you noticed, some of our members left. So if you're feeling like being part of this, please let us know. You have the email of TMS-Cushman seminar, so well, you're welcome. You know that. Okay.
Okay.
Thank you very much.
Everyone.
Bye-bye.